So this is lecture 21. Our goal for this lecture is to give a proof of the following proposition. This proposition 49, that we define these three rings Z1, Z2 and ZP. They're all equal. Okay, and just before giving the proof, maybe just a reminder from last class, the last lecture, what these rings are. So QP was this quotient of C by N, where C was this Cauchy sequences AN, and again Cauchy always means with respect to the p-adic absolute value, with each of the ANs they belongs to Q. ZP is the valuation subring of QP. Now Z1 was defined as CZ modulo NZ, and again N just denotes the ideal of null sequences. The property that the limit as n goes to infinity of AN equals 0. Now CZ was again the ring of Cauchy sequences AN, where now each of the AN belongs to Z, and Z2 again was this quotient Z localized at CZ localized at P modulo N Z localized at P, where now we are considering Cauchy sequences AN with the property that each AN belongs to Z localized at P. Okay, and last class we saw this inclusion, an element of Z belongs to an element of the localization Z localized at P, and we saw that the p-adic absolute value of a sequence where each element of the sequence belongs to Z localized at P, that's positive, that's non-negative. So we have these inclusions, Z1 sits inside Z2, sits inside ZP, and so to prove the proposition, we need to show the inclusion that ZP sits inside Z1. This is what we need to show, and so take an arbitrary element alpha in ZP and consider sequence AN be a Cauchy sequence. Again, Cauchy always means with respect to the p-adic absolute value in C, lifting alpha, and again here each AN is a rational number. Now, without loss of generality, assume that this sequence is not a null sequence, because if it was a null sequence, then then alpha just equals 0, and 0 belongs to every ring. So there's nothing to show if alpha was 0. So without loss of generality, we'll just assume that the sequence is not a null sequence. And again, by lemma 43, there exists an n naught such that the p-adic absolute value eventually stabilizes. So the p-adic absolute value of AN equals the p-adic value of AN naught, and those are not 0 for all indices little n larger than n naught. But what's the p-adic absolute value? It's 1 over p times raised to the valuation. And so this just means that the p-adic absolute values of AN matches with the p-adic absolute value of AN naught for all n larger than or equal to n naught. But since the sequence, this Cauchy sequence, lives the element alpha in ZP, and since ZP is the valuation ring of QP, these valuations in the previous paragraph, these must be non-negative. So we get that the valuation of AN, which in fact equals the valuation of AN naught, since we are looking at elements of ZP, this must be larger than equal to 0 for all n larger than equal to n naught. Okay. Now each AN belongs to Q, so you just write AN as a fraction. You collect all the powers of P, and so you write P raised to the valuation times xn over yn, with the property that these xn's andyn's, they belong to Z and they are co-prime to P. So the GCD of xn and P, the GCD of yn and P, they are both 1. And for all little n larger than or equal to n naught, we have that the p-adic valuation of AN is in fact greater than or equal to 0. Now we have that yn and P, they are co-prime. So by just elementary number theory, if you want the Euclidean algorithm, there exists an integer let's call it un, such that an times yn is congruent to 1 mod p to the n. So I'm just finding an inverse for yn in z mod p to the n, and I'm using the fact that yn is co-prime to p. That is, there exists integers, say un and dn, such that 1 minus un times yn is some power of p. So p to the n times dn. Now construct a new sequence from this. So write bn. So if the indices are less than n naught, I don't have any control, so I'm just going to define sequence to be bn to be 0 if the index is less than or equal to n naught or less than n naught, and if the index is larger than or equal to n naught, well, I want it to be close to an, so I want to be close to this expression an equals p raised to the valuation of an times xn over yn. I really want this sequence, this expression to be an integer, but what's preventing this expression to be an integer is this denominator term 1 over yn. So I don't really like 1 over yn, and I want to somehow make this an integer, and I'm going to make use of this un. So un almost behaves like 1 over yn, but only modulo p to the n. So I'm going to make use of this un. So I'm just going to replace 1 over yn with un. So I'm going to leave all the other terms as it is. So I have p raised to the valuation of an times xn, and what's remaining is 1 over yn, but I'm going to replace that with un. Okay, and the claim is that the limit as n goes to infinity of an minus bn, this is in fact a Cauchy sequence, and it's in fact a null sequence. Again, when I say limit, I am taking the limit with respect to the p-adic absolute value. Again, to check the proof of the claim, it's enough to understand the p-adic absolute value of the difference, but the claim is about a limit, so it's enough to study this difference eventually. So I'm just going to look at all the indices that are larger than or equal to n naught. So whenever this index little n is larger than n naught, we have that an minus bn is the p-adic absolute value of an times xn over yn. And what's bn? It's the p-adic p raised to the p-adic valuation of an times xn times un. So if we collect the common factors, then what you get is an expression that looks like 1 over n minus un. So again, if you collect all denominators and the common terms, you get an expression that involves 1 minus un times yn. But we just saw that 1 minus un times yn is this power of p to the n times dn. So substituting this expression back, you get p raised to valuation of an times xn over yn times p to the n times dn. Okay. So if you just collect all the powers of p, you get p raised to the valuation of an plus n times dn times xn over yn. Okay. So this expression is nothing but an minus bn. And here again, let me remind you that xn, yn, and dn, they're all integers. And yn in particular, the denominator, is in fact coprime to p. So now if you look at this expression, and if you want to compute the valuation, so in fact, so what this means is that for all indices larger than n naught, the p-adic valuation of an minus bn is larger than equal to n plus the p-adic valuation of an. And so in particular, this is larger than equal to n. And so in other words, for all indices little n larger than n naught, the p-adic absolute value of the difference is less than equal to 1 over p to the n. And so this is enough to prove the claim, since now the limit as n goes to infinity of an minus bn in p-adic absolute value, this goes to 0, as the limit at n goes to infinity of 1 over p to the n goes to 0. So in other words, what the claim has shown is that the sequence, the limit as n goes to infinity of an minus bn, this is 0. And hence, the sequence an minus bn is a null sequence. And hence, if you look at the sequence, say bn minus an, that's also a null sequence, since I'm just multiplying by minus 1. And hence, well, the sequence bn is nothing but the sequence an plus the sequence bn minus an. Now each of the terms in this sum, by assumption, the sequence an is a Cauchy sequence, so it belongs to C. The difference bn minus an, we have just shown that it's a null sequence, so this also belongs to the ring of Cauchy sequences. So the sum is also Cauchy. So the sequence bn is also a Cauchy sequence. And so if you look at the equivalence class, so consider their images in C mod n, we have that the equivalence class of bn, the sequence bn, equals the equivalence class of an, but the equivalence class of an was just alpha by construction. But however, every element bn of the sequence belongs to Z, and hence the sequence bn in fact belongs to Cz. And so this equivalence class of the sequence belongs to Cz mod nz, which is what we call z1. So what we've shown by our assumptions, so this equivalence class of Bn is nothing but alpha. So what we've shown the reverse inclusion that this element alpha, which belongs to Zp, in fact sits inside Z1. And so this completes the proof of the proposition as we've now shown that Z1 equals Z2 is in fact the valuation subring of QP. Okay, thank you.